The next piece is to incorporate Taylor series in this. So I just want to point out that just as in the real case, so just as in the real case in Calc 2, basically, what's going to happen is we're going to take our function f and we're going to look at the power series centered at z naught. So this is c sub n, z minus z naught to the n. And this is, if you just think about what this is by definition, this is C0. So this is C0 plus C1 times Z minus Z naught plus C2 times Z minus Z naught squared plus C3 times Z minus Z naught cubed, and so on. And so if we think about what this is going to be, well, we know that the derivative is going to, so what we proved in the previous video, or 2 videos, is that we can differentiate term by term inside the radius of convergence. So I'm going to just take that fact for granted now because we just proved it. So the derivative of this quantity is going to be, so the derivative is C1 plus 2C2, that's a C, so 2C2 z minus z naught to the first plus 3c3 z minus z naught squared, and so on. And so that tells us that f prime of z naught is c1. I forgot to mention that before. Let me add that in here. So I forgot the punchline of what I was doing before. But f of z naught is just c naught. Because if you plug in z naught for all the z's, all those go away. The only thing that remains is the first term. Okay, and likewise, the first derivative at z naught is c1. You can show that the second derivative at z naught is 2c2. The third derivative at z naught is, it turns out, 6c3. The fourth derivative is 24 c4, and of course this is 24 is 4 factorial, 6 is 3 factorial, 2 is 2 factorial, 1 is 1 factorial, and 1 is also 0 factorial. Okay, so in general what this means is that c sub k is going to be given by, well, let me say what I said here. The kth derivative at z naught is going to be given by k factorial times c sub k. And therefore, we get the kind of remarkable result that these coefficients c sub k are always going to be of the form that they're the kth derivative of our function at z naught divided by k factorial. Okay, and so if f has a power series, it must be a power series that looks like this. That'll be the sum is k goes from 0 to infinity of the kth derivative at z naught over k factorial times z minus z naught to the k. Sorry if I used n before. I probably am interchanging n's and k's, but it's just a dummy variable anyways. So it's the same whether I write n or k. So this is now Taylor's theorem for complex functions. Okay, and so that's how that works. So that's the Taylor series of a function. All the usual suspects have the same Taylor series. You have to do a little bit of work to do this, but it turns out that the same Taylor series are true. So we even talked about this a little bit back in chapter 7, but e to the z is z to the k over k factorial. Okay, so that's how that works. Sine of z is going to be the usual negative 1 to the k, z to the 2k plus 1 over 2k plus 1 factorial. And you can establish this either by first principles, so just calculate all the derivatives, which you know how to do, or you can expand it using the exponentials, and the book goes through that. Cosine is also the same. So cosine of z is the sum from k equals 0 to infinity of negative 1 to the k, z to the 2k plus 1. I don't know why I put parentheses there. And divided by, not 2k plus 1, z to the 2k, divided by 2k factorial. Okay, so all the usual suspects have the same Taylor series for complex functions, complex inputs, as they do for real inputs. I might also talk a little bit about the binomial theorem and maybe a few other examples of Taylor series. So I'll do that in an upcoming video.